Hello, welcome you all. Today we will discuss the two basic waveform in different application of the electronic circuit, that is square wave and the pulse wave generator. Now these two waveforms are generated by different electronic circuits or the block diagram management we will see in the later section. Now the application of the two waveform are very specific. In the case of the first pulse wave generator, it is used in the multivibrator circuit or in the digital circuit as a triggering mechanisms. That means you can see in the multivibrator circuit there is a trigger needed for that the circuit to operate. Now this trigger is actually produced by a very short duration pulse. So that is the use of the pulse circuit. Now as in the case of the square wave circuit, it is most commonly used as a message signal in the communication purpose. That means in the different communication purpose, as a test signal it is used as a message signal, as well as it can also be used as a high frequency square wave, can also be used as a carrier signal also. Now in this section we will discuss the duty cycle of these two waveform, the definitions and the expressions of this or the value of the duty cycle of this two waveform. Now the definition of the duty cycle can be extended or can be expressed in two different ways. First of all, you can see on the screen that the duty cycle can be expressed as the ratio between the pulse width and the period. That means how much time the pulse is on and with the period of this waveform. Now in the case of, you will see in the next page that in the case of the square wave the duty cycle is 50%. That means it is 0.5. okay, now it can be so, as we can see that the duty cycle definition of the duty cycle is ratio between the pulse width and the period, and also duty cycle is 0.5 in the case of the square wave. So you can say that the pulse width is t by 2 to the total pulse width or the period, that is t. It can be expressed in that way. And the next definition, in the indirect definition, that means if the duty cycle is 0.5, then duty cycle is defined another way, that is average value by the peak value. Now as the duty cycle is 0.5, then easily we can say that the average value is half of the peak value in the case of square wave. Now duty cycle, you can say that the duty cycle, I have already said the duty cycle can be expressed as a percentage term. So you can see here that is written 0.5, and also in the next word it is written as percentage term. So as a general definition, duty cycle can be expressed as a percentage. So the foremost thing is here is that the duty cycle is defined in the two ways. First of all, it is defined by the pulse width divided by total period, and it is also defined in an indirect way, that the average value by the peak value. This is the most uncommon expressions of the duty cycle. In the next page you can see the two waveform of, I can zoom out so that you can see very easily that here you can see that 1 minute. Okay, so here you can see that the waveform of these two, that is the first one, this is the square wave, and second one, this is a pulse. Okay, now in the case of the square wave you can see that this is the square wave. Okay, so here you can easily see that the peak value, that the average value, this is the average value for the case of the square wave, and it is expressed as half of the peak value. That means peak, whatever may be the peak value, that is average value is half of the peak value, but is base is, that means the reference level is 0. okay, and it is this positive half cycle, it is this negative half cycle. but it in the case of the square wave, this is the positive half cycle and this is the negative half cycle. It does not means that the total value of this waveform, suppose this is a, you don't think that this is positive and this is negative, area is both of these two is positive and negative, so it does not mean that the total area is 0. It is not happening like that. The amplitude and time is actually multiplied in a most common way and it is integrated over the period. That is the total value is, it is divided by t. From that expression we can calculate the average value of any waveform. You can see the expression in the signals and system course in your syllabus. So next is your pulse. Now you can say that the pulse is actually defined, it is not like the square wave, that is upon the 0 value it is oscillating. Square wave is actually oscillating between the 0 value, that is it is sum of the positive half cycle, sum of the negative half cycle, like that. But in the case of the pulse, it has some sort of reference level. From that reference level is value is calculated. Okay, and it has some on period and it has some off period. That is the call pulse on period, and you can see that this is the pulse off period. Okay, now you can see that here is the problem comes, that the average value and the peak value. Now from here you can conclude that the average value is just the half of the peak value, just middle of that, but it is not at this way it is calculated. I have already said that the total area is first calculated. Okay, total value of this waveform is first calculated, then it is divided by t. So in that way, that means it is whatever may be the area of this two waveform, that is first calculated, then it is divided by t. That means the total duration. Okay, that means if the waveform is some sort of finite value over the duration 0 to t, some sort of finite value, that is it is some sort of area over that period, and the total period is t. Over that period the area is actually 0. Now from that roughly you can see that as the calculative measure of the value is, total value of this waveform is 0 to integration t a into dt, and also the total value is total duration is t. So as the upper section is integration limit t, so there is some sort of, and the peak value we can see that the peak value here is a, so it is t and it is peak value then divided by t. So average value is calculated like that, not it is that this is your waveform, you can, this is your 0, this is your a, so it is not that the average value is a by 2. Average value is calculated by some sort of mathematical expression, and this is your mathematical expressions. Okay, so I am again repeating, the total area is first calculated, then it is divided by the total time period. So that's why the average value for a pulse is t by t into peak value. That's why it is t by t into peak value. It means whenever you calculated the area, the first, the 0% is actually not accounted because it has area 0 and amplitude 0, that's why it must be area 0, but whatever must be its value it is holding during the on period, and that duration is t, so that's why it is t by t into peak value. Okay, I hope you will get that. You will must find some sort of expression in your signals and systems course. Okay, the average value, calculation of average value of any particular signal, you can find it very easily. Next, so the duty cycle of the pulse is another definition I have said that it is the indirect definition, average value by the peak value. So the average value peak value ratio is t by t. Okay, now the duty cycle is pulse may be varied between 50% to 95%, whatever may be our requirement according to the application of this pulse. For that purpose we are defining the on period of the pulse, and from that we can say that the duty cycle is varied between 50 to 95%, but in the case of the square wave it is always 50%. because the value, whatever may be the value you are calculating, that value is always 0.5. okay, hope we will get that. Next we will discuss some of the characteristics of the pulse. So first of all, you can see that this is the actual waveform of a pulse. Okay, now from this actual waveform of this pulse, there is a different characteristics or the different terminology associated with this pulse waveform. You can see this is the your amplitude, this is your pursuit time, this is your rise time, this is your settling time. In your network course you will find this term. This is your baseline, this is 0 volt, this is base offset, this is rounding, this is fall time, this is medium offset, this is trailing edge, this is droop, this is overshoot. You will find the term overshoot in your network course. The first term is your pulse rise time and fall time. Rise time is fall time is defined by the pulse go from 10% to 90% of its amplitude, and the fall time is just the reverse of that. That means whatever may be the time required to pulse from go from 10% to 90%, that is defined by rise time, and also whatever the time it is going from 90% to 10% of its amplitude value, that is defined by fall time. Next is your linearity. You can see that this is the next time is your linearity. So linearity, you can say that the linearity of the pulse is deviation from its, wait a minute, linearity of the pulse is the deviation from an edge, that means from the straight line. That means this is the actual pulse waveform, but this is not all the case from the practical purpose. So whatever may be the value that is deviating from that, okay, so that is the expression of your linearity. Next is the settling time. Settling time, it is the positive and the negative peak distortion excluding the overshoot. Okay, so whatever may be the overshoot value, that must be excluded from the settling time. So whatever may be the value it is required to settle the final position of this waveform peak value, that is expressed by the settling time. Next is the pulse droop. It is the fall is amplitude with time, and the pulse rounding is the curvature of the pulse and the leading and the trailing edge. Okay, this is your trailing edge and this is your leading edge. So that is defined by pulse rounding. There is different sort of characteristics. So pulse width. So pulse width is defined by this, whatever may be the width of this pulse. You can see that this is the width of the pulse. Duty cycle, I have already defined the duty cycle. Not all are important, but some of the terms that important is pulse rise time and fall time. Linearity is also important, that is the deviation from the actual pulse. Settling time is also important, it is excluding the overshoot. Maximum height immediately followed the leading edge, that is also called the pursuit value. Okay, this is your pursuit. You can see that this is your pursuit value. This is your baseline offset. Okay, so that's all. You can see the waveform very accurately, and you will see different characteristics. That is very straightforward. And from the next we will discuss the block diagram arrangement of the pulse wave generator. Thank you.